Now that we understand the why of HPC, let's take a brief look through the history of supercomputers, and in particular, let's look into the high performance aspect of supercomputing. We'll start with the famous supercomputing quote, and I'd like you to consider your own answer to this. If you were plowing a field, which would you rather use? 2 strong oxen or 1,024 chickens?
Fight!
The obvious answer is 2 strong oxen, and this was the point that Seymour Roger Cray was trying to convey. Now, Seymour Cray is known as the father of supercomputing, and he was a supercomputer architect responsible for many of the fastest early supercomputers in the world. The secret to Seymour Cray's success was that he realized that there's more to performance than simply a CPU. One of the key realizations was that data bandwidth needed to be high enough for the processors to never be waiting for a stream of data to arrive. Nonetheless, the main design principles of the early supercomputers were still essentially single monolithic supercomputers. Just like the Cray 1 supercomputer that I'm standing next to in this picture, which is housed at the National Center for Atmospheric Research in Boulder, Colorado. A fun tidbit is that NCAR is responsible for the WRF model and datasets that you may need to implement as one of your challenges. The model of building faster and more powerful CPUs worked very effectively for years, but eventually the advancements in technology caught up with the physical limitations of the electronics. To put it simply, CPUs just couldn't go any faster, and there were too many memory traffic jams on a single bus. It was just no longer efficient or cost-effective or even possible to keep pushing the performance of a single CPU core. So the natural progression was to develop multi-core CPUs. Since it was becoming increasingly difficult to push the performance of a single CPU, it became significantly cheaper to build these multi-core systems. While Cray's systems also embraced the multi-core approach, they still tried to keep everything within a single computer system, which invariably led to the traffic jams. The 1024 chickens approach was rather to take a large number of comparatively slower systems and link them together over a network interconnect. So Cray's analogy really was appropriate. At the time, classic supercomputer was a large, powerful system. It was effectively built like an ox, both in size and in power. The alternative approach was an interconnected cluster of many much smaller systems. Essentially, these would have been built like chickens in size and power when compared to the oxen. But what they lost in individual performance, they made up for in collective performance. Not only that, these multiprocessor massively parallel processing systems were significantly cheaper, and Cray did push back with that famous agricultural quote, but unfortunately for Cray, the writing was already on the wall for his model of supercomputer design. Meanwhile, some underfunded contractors at NASA's Goddard Space Flight Center built their own supercomputer using commodity off-the-shelf hardware. At the time, it was 16 486DX processors, and thus Beowulf was born. The creators of Beowulf, Becker and Sterling is pictured here sitting at my desk, they had unwittingly created the most popular supercomputer design, a Linux-powered Beowulf cluster supercomputer. Beowulf formed the model for modern computer clusters using high-speed interconnects. With this development, the symmetric access to memory, that is, global shared memory, was also replaced with distributed memory, with hundreds or thousands of processors working in harmony using distributed parallel programs. This new model effectively and dramatically shifted the mindset from gigantic oxen plowing the field to this thousands of chickens plowing the field, which seems completely counterintuitive. With Cray's so-called old model, systems just became expensive to build and expensive to run, and component bottlenecks increased as speeds increased. The new model, or the solution to that, were the Beowulf clusters. That was comprised of commodity hardware that you could procure off the shelf that provided enterprise performance. Whereas the old model was traditionally the scaling up model, where you made faster systems, the new model was the scaling out model, where you could add more systems to your existing HPC system or cluster.